Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today I want to have a look at something that we're all familiar with, but really don't understand that well, and that's time. Studying time tells us an awful lot about the orbit of the Earth around the Sun and the rotation of the Earth about its axis. And a great visualization of this process involves this instrument right here, the astrolabe. So let's cue up the music and get going. Now, many people in my generation, when we want to know the time, we just look down at our wristwatch. This happens to be mine. Others will use an Apple Watch or the display on their smartphone and know what time it is to the second. But centuries ago, that was not as easy a task. For example, this device is called a heliochronometer, and it's basically a modified sundial. And it's got a couple of very interesting features, interesting enough that I think I may build one of these. But there's a couple of things that you'll notice. The sundial has to be laid into position. It's actually surveyed into position. And then what it does is it takes the rays of the sun and projects them onto some sort of a display where you can read the time. This one is rather interesting because, as you see, that's a solar anemometer. And the way this sundial operates is that there's a small hole in that paddle, and as you see, there's a large shadow with a bright dot of the sun. The entire sundial is rotated until that bright dot of the sun hits the solar anemometer at an appropriate place for the time of year. Then all you have to do is read off the time. This is accurate to about 1 minute. But sundials have a little bit of a problem. You have to orient them properly. They have to be oriented to your latitude and to true north. And once you have them set in, you don't really move them very much. What they needed was something that was very portable. And that's where this device comes in handy. This is an astrolabe. Traditionally, they were made out of brass and they were quite heavy, but they were about 8 inches in diameter, and it was something that you could actually move around with. So the subject of today's video is how do you tell the time on an astrolabe? Now, this is a wooden astrolabe that I built from a kit. I had a little fun building it. We did it online. A traditional astrolabe is made out of brass and kind of looks like this. It's got a movable ret. It's got a pointer, and it has a couple of sights. But we're going to use the wooden one because A, I built it, and B, it's very clear. You can see the lines very nicely, and it's got a couple of features that that brass one doesn't have. The brass one has some features that this one doesn't have. There were several different designs. Now, one interesting feature about astrolabes is that they were originally set up under the zodiacal calendar, according to the signs of the zodiac. So when you're going to use an astrolabe to tell the time, the very first thing that you have to do is you have to figure out what today's date is in the zodiacal calendar. So let's go ahead and do that. Now on the back, you'll see the signs of the zodiac. Here's Capricorn, Sagittarius, Scorpio, etc. And underneath it, you'll see the months of the modern calendar. Here's January, there's December, that's February. Now each sign of the zodiac has 30 degrees assigned to it out of 360. There are 12 signs of the zodiac, 30 degrees each, 360 degrees in a circle. So the very first thing that we have to do is we have to figure out what is the zodiacal date for today's date. And that's done right here. Let me put this up so you can see it a little bit better. So this right here is January. And as you can see, today is January 26th. That makes this the 7th day of Aquarius. The next step is that you have to actually take a sighting of the sun. And the way that you do that is you hold the astrolabe up by the ring, let it free hang with gravity, and that will establish a vertical. Then you'll notice that you've got a couple of sights right here. You've got some notches, and then you also have some holes in the sight as well. However, you don't want to look through the astrolabe straight into the sun. If you want to go blind, that's how you go blind. Just don't do it. So what you do is you hold it over your shoulder. You let the sun shine through this little hole in the sight right here and form a shadow on the sight down at the bottom. Like that sundial, you'll get a shadow with a bright sunspot in the center of it. So you get that shadow onto this plate down here and line up the holes. Let me show you how that's done. Now this was a shoot that I did earlier today. As you can see, there is a hole in that front sight. There's a notch in the front sight, and you can see the spot of the sun. It's just off that hole. So it needs a little tweaking on the alignment, but that's getting very close. Now once you have the sunspot lined up with the hole, you're done. Because once you have that sunspot lined up with that hole in the sight, you have the altitude of the sun. And in this case right here, you'll see it's 24 degrees. Now the next thing that we'll do is we'll turn the astrolabe over onto the side that has the ret on it. Now here you'll see a series of grids. This lower grid is dawn. That is the horizon line. Now each of these demarcations coming up are 5 degrees. So that's 5, 10, 15, 20, 25 degrees. What we're going to do is we're going to line up the 7th of Aquarius with the 25 degree marker. Then what we do is we take our ruler and we bring it over to the 7th of Aquarius. So there's the 10th, 9th, 8th, 7th. And then we simply read off the time. And when we do that, we find that we have 10, this is 30, it's one hash mark back, so that's 10:25 a.m. But let's pull up Stellarium real quick, and we're going to see when the sun was 25 degrees in altitude today. It's about 11:18 in the morning. So why is there a difference in the time on the astrolabe compared to the time on my watch? Well, that has to do with solar time versus civil time. Well, my time zone is centered at 75 degrees west longitude. That's basically Albany, New York. I am 9 degrees west of that position. So as a result, solar noon in my position will not be 12 o'clock. It'll be 12 o'clock in Albany, but I've got to wait 36 minutes before I have solar noon at my location, so it'll be 12:36. So let's go ahead and go over to date and time and see the astronomical data for today. So here's the solar graph for Gaylord, Michigan. Now let's go down to today's date, January 26th. Now solar noon is when the sun is 180 degrees due south of your position. It's basically when it passes your meridian or your line of longitude. And according to this, solar noon in Gaylord, Michigan is at 12:51. But we just got done looking at solar noon in Albany, and we realized that our solar noon should be 12:36 p.m. Why is it 12:51? Well, that has to do with something called the equation of time. So let's go back to that heliochronometer and have a look at something, maybe a little detail that we may have missed. And here it is right here. This is the solar analemma. This is related to what's called the equation of time. Now the Earth orbits the sun in an elliptical orbit. It's closest to the sun on January 4th, and it's furthest away on July 4th. Now it's not that much of a difference, only about 3%, but it is enough to have an effect on our timekeeping. Well, let's go ahead and see why that is. A lot of people seem to think that the Earth rotates once every 24 hours. That's not true. It's 24 hours from noon to noon at any given spot on the Earth. So why is it 24 hours from noon to noon? Well, if it was 12 noon for this individual right here, 23 hours and 56 minutes and 4 seconds later, if the Earth was not moving, the Earth would completely rotate around and be in exactly the same spot, and it would be 12 noon again. It also goes 1 degree in its orbit around the sun. So as a result, if you were to look at what they call the sidereal day, which is the 23 hours, 56 minutes, 4 seconds day, that would be if you imagined looking at a star out in the very far distance. As you know from our talks about celestial navigation, light from the stars arrives at Earth in parallel. So if you were to look at that same star from this position and from this position in our orbit, it would come in parallel to this line right here. So going from this point around in one rotation back to the exact same position in reference to this star is called a sidereal day. Now at the end of the sidereal day, we've also moved 1 degree in our orbit. So the sun is no longer here. Now the sun is over here, and it's changed by 1 degree. it won't be noon at this spot because you've got to come over another degree. So the Earth needs to rotate another 4 minutes to go that 1 degree to again point at the sun. Now, as a consequence of that, we can tell that the orbit of the Earth moves in that direction. If it moved in the other direction, one sidereal day would bring us back to this position right here. But this right here, 1 degree to the west, would be our noon. And as a result, from noon to noon would be 23 hours, 49 minutes, and 4 seconds, because we'd have to shave that 4 minutes off. So simply by orienting ourselves to the background stars, we not only can tell that we're rotating on our axis, we can even tell that we're orbiting around our sun. But what about this 15-minute variation in solar noon? Well, one of the things that causes that is the orbit of the Earth, because the Earth is not in a perfectly circular orbit. What we do is we're in an elliptical orbit where we have a period where we're closer to the sun and a period where we're further from the sun. We're closest to the sun on January 4th. We're furthest away 6 months later in July. Now, as I said earlier, it's only about a 3% difference, but it's enough that under Kepler's laws of planetary motion, we are going faster here than we are here. And that increase in angular velocity as we get closer to the sun and the decrease in angular velocity as we get further away from it means that our solar noon varies by as much as 15 minutes before and after. Now here in January, you'll notice that the sundial is slower than civil time, which is watch time, and it's about 15 minutes. This is the 15-minute mark right here. And as you see, we're about right here, so we're at about 13 minutes. So as a result, we have to add 13 minutes to the 36 minutes we're delayed behind Albany, New York. Now, there are a couple of times during the year that sundial time and watch time equal each other, but it generally varies.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Above the science guy, above the science guy.